Hi, everyone. This is a group project for Clay and Ihor, and our project is about explaining recurrent neural networks. We believe that our project is most suitable to model track because our core contribution is really about the model. We're essentially trying to better explain how recurrent networks work in general, not specifically limited to certain types of neural networks. Another point we would like to mention is that during the class, we've seen many examples contributing to interpretability of convolutional neural networks, but we didn't see any good examples for recurrent networks. We found this as a problem, wanted to tackle this, and essentially suggest a novel approach to interpret recurrent neural networks in general. So in this interactive application, you'll be able to explore why RNN produces one or another output and what makes difference for the model in the input. The model that you'll explore is a simple RNN that was built on IMDb reviews binary classification data set with target value positive and negative reviews. To explain a little bit about our choice of data set, we chose IMDb reviews mainly for two reasons, because it's a simple binary classification task, and it's also a very classical data set widely used on sentiment analysis with many verified models in terms of performance. We want to emphasize that the task of our project is about model interpretability, not model performance. And so the fact that we didn't have to focus on model performance at all really came to us as natural. And this was why we chose this IMDb reviews data set. To explain our model a little bit, our model consists from embedding layer, LSTM or long short-term model, single hidden dense layer with 64 neurons with ReLU activation, and dense output layer with a single neuron. As you can see, this is a really simple deep neural network, and we intentionally chose the simplest architecture that would give us a decent performance. Again, because the main task of our project is about model interpretability. And on the trained data, our model gives about 80% accuracy. The proposed framework is illustrated on specific and considerably simple model. However, it is a very general framework and can trivially be extended to larger and more complex models. Okay. Now we'll get into some insight about how the model works by observing which words contribute to the decision, whether to output positive or negative. Below, you'll see 5 sample reviews from the example dataset with prediction, confidence of the prediction, and visualized word impact. So here, so first of all, it's a disclaimer that the model performance is not perfect. So you might agree with certain predictions and you might not. But again, this is not the issue for us because our purpose, the main task of this project is on interpretability. So here, coming back to the color representation. So the color here, the positive color represents the positive sentiment. And the color red means negative, and the gray colors here means neutral. Impact on model's prediction. Again, this means how model's prediction and confidence have changed after seeing a particular word token. So for example, in this example, seeing the word magical contributed a lot to this model making positive sentiment with prediction 0.21. And opacity here represents the strength of the impact. The higher the opacity, the more impact the word had. So here, for example, the unbelievable here, the word token here has the highest opacity, meaning that it contributed to the most to this example being classified as negative. Whereas the words such as were, as, or actors didn't contributed much less than this word token unbelievable. So from here will take on and explain about the training.
Yes, so we believe that while observing how model works now is important, it's also really crucial to understand how model arrived at that state. So to do so, we visualize the training process in the same way. And here we can see how model was learning the patterns. So it started to be pretty random. And we can see that it basically learned to take to learn that words really and cool have a positive impact, although it's really small for this particular sentence. And that word great is in the most of focus. It also learned that the word authors is negative, which can be explained by either that model learned something that it shouldn't learn, which is a good point that we can take out of this example, or maybe it's that authors was not in our training data, and it's an unknown word for the model, and it by default assigns a negative probability to it. So this is one takeaway. And next, let's consider something like simple, this movie was boring. And if we type this, we'll see that model learned to take into account only the word boring, and those words are completely ignored. We can also note that it's a very high probability of being negative. It's 56%. And because those words are completely ignored, we can check this by inputting something similar, like this film was boring. And we'll see that we'll have exactly the same pattern. And even more, we have exactly the same probability. However, this can raise a concern. What happens if we have this was not boring? Like ideally, models should understand this word not, but we can see that it has not learned this, and over the training process, it was ignoring the word not as well. And we can see exactly same probability. So what happens here is that model only takes into account the word boring itself. Next, we also visualize a feature space and how it's transformed while being passed through model layers. So this plot, it represents the learned sentence embeddings. This plot represents the output of LSTM layer with an input of sentence embeddings. And this plot represents the output of a dense layer with an input of LSTM outputs. So we can see how the transformation that model was creating evolved over the epochs. And also we can see that model basically learned to make kind of a linearly separable feature space out of those embeddings, which themselves are in some way distinguishable, but still not really separable. One important part that we can see here is that those two charts, they're very, very close in terms of the pattern, shape, and errors that are considerably separable. So for instance, this can give us a hypothesis that maybe this dense layer is not really required. So maybe we can build a model that will have comparably same performance without this layer. We can also we also see our review here, and we can see some close reviews if we hover here. And this can give us some understanding about how the model works. So we believe that those two visualizations are important in understanding how recurrent neural network reads the sentence. And we hope that this project will help people understand better how their model function and potentially eliminate some biases or some inefficiencies. Thank you for your attention.